Next up is the sulfonation reaction. I would challenge you to pause this video and see if you can draw the reaction of SO3 plus sulfuric acid. So you have to be able to draw what SO3 and sulfuric acid look like to form your electrophile and your base. So the question you always want to ask yourself when you're looking at a reaction is who has electrons and who wants them. The proton is going to be given up, so that's going to be who wants them, and who has them are all these bonds between sulfur and oxygen. So if you go through this again, you find here's where our electrophile is, and here's where our base will be that we'll use in the overall mechanism. Again, I would encourage you to pause the video, try and see if you can draw the entire mechanism first, and then go back and watch and see if you got it right. So just like the other mechanisms, who has electrons and who wants them? The benzene has electrons. The SO3H is our electrophile, that's who wants them. So a pair of electrons comes out from the aromatic ring to the sulfur. So we get our intermediate, then the HSO4- comes in, deprotonates again, causing an electron pair here to go back and reform the aromatic ring again. All right, we'll keep going with new reactions, and now we'll look at a Friedel-Crafts alkylation reaction. And again, I would challenge you to pause the video, see if you can draw the reaction with chloromethane plus aluminum chloride to form your electrophile. Then once you do, you can draw the reaction of the benzene with that electrophile. It's really almost the same as the reaction between Cl2 and FeCl3, or Cl2 and AlCl3. The electron pair from chlorine will attack the Lewis acid, or the electrophile over here, in the aluminum chloride. Now there are two different ways to draw the mechanism. So far we've been showing our intermediates breaking apart first. If this breaks apart at this stage, we'll end up getting a methyl cation plus AlCl4-. This is a highly unstable cation, so it's not very likely that this would happen. So there's two different ways to draw the mechanism. One is to draw it this way, which may not be the most accurate, but will still work and give you the right product. The other way to draw the mechanism is to draw the benzene ring reacting with the intermediate directly. If you do that, you can see at this point that these two intermediates are exactly the same. So the rest of the mechanism is exactly the same also. So if you're asked to draw the reaction of benzene with propyl chloride and aluminum chloride, you should be able to guess that you'll probably get the same thing. So you should get propyl benzene. However, that's not quite the case. You actually get a mixture of propyl and isopropyl benzene. Right, so when things don't happen the way that we expect them to, we have to go back and try to draw mechanisms that account for the different types of products. The first product, the propylbenzene, is fairly easy to account for with a standard mechanism. So if we make the primary carbocation, the benzene ring reacts with that. And aluminum chloride comes by, takes off the proton. We get the first product, no problem. So the question then becomes, how do we get the second product? Well, I would hope that when you saw this primary carbocation here, you would think, wow, that's not very stable. And it's certainly not. If we have the primary carbocation, it can rearrange very easily through hydride shifts that we talked about last semester to form the more stable secondary carbocation. So if that happens, and now we have our benzene ring reacting with the more stable secondary carbocation, it will form the isopropyl benzene product. That's how we explain the two products that we get through Friedel-Crafts alkylation. Now here's your chance to prove that you're a real organic chemist. Try to see if you can write out the reaction to form the electrophile between your acyl halide and aluminum chloride first. Then once that electrophile is formed, write out your reaction for benzene reacting with that electrophile. And then of course with the AlCl4- base to come by and deprotonate it to reform aromaticity. So pause the video and see if you can write that all out before continuing. One of the things that I love about organic chemistry is the logical nature of it, and how so many things, once you've learned one reaction, you can determine the results of many other reactions. So we know that aluminum chloride already is a Lewis acid, and we know that chlorine has lone pairs of electrons. So just like with Cl2, just like with the Friedel-Crafts alkylations, electrons come and attack the Lewis acid, aluminum chloride. To form an intermediate. Now, intermediate can again be broken down the same way. Electrons move over to get rid of the positive charge on chlorine. So the product of this part of the reaction is our electrophile, our acyl group. And the other thing that's left is the base, the AlCl4-. So again, we'll go back to the benzene and react that with our acyl group. Form our intermediate, which then again will react with our base, and is deprotonated to reform aromaticity.